Today we'll be discussing the all-important topic of IPv4 addressing. You all might be noticing some sort of addresses like this during your interaction with your network. For example, the first one is a IPv4 address, the second one is a IPv4 address, the third one is a IPv6 address, the fourth one is a subnet mask. This sort of addresses you might have noticed while doing some sort of troubleshooting in your network or at some other places. Today we'll be dissecting the meanings of such addresses. If you want to have a look at the IP address of your computer, there is a command which you can run in your command prompt if you are running Windows. Let's look at it first. Run your command prompt. Simply type ipconfig/all, ipconfig /all. If I run this, it is showing me my IPv4 address. Look at it. IPv4 address is this one. It is showing something like subnet mask. This one. It is showing some IPv6 address. This one. So this is how you got to know your IPv4 address and IPv6 address in your system. Simply run ipconfig/all. This is when you run Windows. The same ipconfig command also works on Mac OS. If you are using a Linux system, you will be using this command ifconfig. So these are different sort of commands that are capable of displaying your IP addresses. So there are the IPv4 addresses, there are IPv6 addresses, and there is something known as subnet mask. When we go further, we'll see that there is something called IPv4 public addresses. There is something called IPv4 private addresses as well. So we will be discussing all these things in this particular lecture. Now, when we talk about an IPv4 address, when you see address, what meaning does it convey? So if I have just an address like this, say this is an IPv4 addresses, is it just a number which is some sort of identification, or does this number give certain information about your system? That means, is this number is helpful in recognizing some aspect of that particular node in the context of the overall network. To understand it, let's have an example. Say I have 3 roads, normal roads, lanes. So this is one road number 1, this is another road number 2, this is another road number 3. So to say this is lane number 1, this is lane number 2, and this is lane number 3. And these are different houses on that lane, and all the houses are numbered. So in the first lane, this is house number 1, this is house number 2, this is house number 3, like this up to house number 14. If you look at it, the lane number 2, there are less number of houses because these houses are little bigger than these houses. And in this third lane, there are houses, again these are bigger than the houses in this lane, so there are still less number of houses in this particular lane. So there are 6 houses in lane number 3, there are 8 houses in lane number 2, and there are 14 houses in lane number 1. Now say I want to create a table to show this information. So I have created this particular table. Say I have 2 columns in this table, a lane number and house number. So lane number 1, house number 1, lane number 1, house number 2, lane number 1, house number 3, and so on up to house number 14. There were 14 houses in lane number 1. Similarly, I have lane number 2, house number 1, lane number 2, house number 2, and so on. And again for lane number 3, all the houses. So I have a table where I have listed all the lane numbers and I have listed all the house numbers. Now say I want to combine both this information. A simple way of combining is something like this. Say I have combined these two, 101, and made an information something like 101. I have combined 102 and this is a combination 102. Or I may want to put some separator between this. Say here I put a separator 1.01 where 1 is the lane number and after the dot 01 is the house number. Again lane number 1, house number 2, lane number 1, house number 3, lane number 2, house number 1, something like that. Some way of combining these two information. So what does this information convey? This information or disinformation? This information conveys in this example 2 different things. The first part conveys the road number or the lane number. The second part conveys the house number. Clear? So in this example, this combined information provides me two different information. One is the lane number, the other one is the house number. Now let us have a networking example. Say we have three different networks. This is a network of an organization. Say this is a small organization where there are a few number of computers. This is a medium level organization which have some more number of computers, and this is a much bigger organization which have a lot of number of computers. And in this network there are even sub-networks. So say this is a network of one department, this is a network of another department of that organization, so on. So in this example we are seeing three different networks: a smaller, a medium level network, and a bigger organization. Okay, just like we had lane numbers in the previous example, say we have network numbers here. So we are denoting this as a network number 1, we are denoting this as network number 2, and we are denoting this as network number 3. Clear? And within this network, say there are computer numbers. So in this example, this is computer number 1, this is computer number 2, this is computer number 3. Here in network 2, again computer number 1, computer number 2, computer number 3, and so on. Similarly for this network number 3. So just like we had the lane number and we had the house numbers, similar we have the network numbers and we have the node or computer numbers. So network number 1, computer number 1, network number 1, computer number 2, network number 1, host number 3, network number 2, computer number 1, network number 2, host number 2, and so on. Clear? Now let's create a table again in the similar fashion. So we have a table here: network number 1, computer number 1, network number 1, computer number 2, and so on, in the similar manner as we did in the last example. Also, let's change the nomenclature a little bit. Instead of network number, let's use the nomenclature network ID, because later on we'll be using this nomenclature frequently. And instead of computer number, let's use host ID, because in a network it can be any node. It need not be a computer, it can be a printer, it can be something else also. So instead of saying computer number, let's use the word host. And instead of using the word number, let's use the word ID. Just the nomenclature, other things remain same. So network number 1, host number 1, network number 2, host number 1, network number 2, host number 2, and so on. And then we have combined this information, again just as in the previous example. So what does this combined number indicates? What information does this combined number provide? So this combined number provides two information. One is the network ID and one is the host ID. So from one single number, one combined number, we are getting two information. What information we are getting? One information we are getting is the network ID, and one information we are getting is the host ID inside that particular network. Similarly, an IPv4 address, or in fact even an IPv6 address, contain two information. The similar two information: one information is the network ID and the other information is the host ID. So whatever IP address you see, whether it's an IPv4 or an IPv6, it provides two information. One information is the network ID and the other information is the host ID. Now remember, the IPv4 addresses are of 32 binary bits. That means the size of an IPv4 address is 32 bits, or in terms of bytes is 4 bytes. The size of an IPv6 address is much bigger. We'll be discussing IPv6 addresses in a separate lecture in detail. So in this lecture, we'll simply concentrate on IPv4 addresses. So in IPv4 addresses, we have a 32-bit string like this. So this is a random example. So in this example, we have taken any random 32 bits. So this is an example of an IPv4 address. So this IPv4 address will contain in itself two information: the network ID and host ID. Clear? Now, when we are dealing with IPv4 addresses, so that we can, as humans, we can easily interact with this number. Remember, it is humanly not possible to remember an IPv4 address in terms of 32 bits. No one can deal with or process these numbers using this representation. So for our help, for the help of human beings, what we do is we divide this 32-bit number in 4 equal parts. Clear? So there are 32 bit. If I divide into 4 equal part, there will be 8 bits in each part. Clear? So we divide this 32 bit into 4 equal parts, and then we'll put a dot in between those four parts. That means we have divided this 32 bit number into 4 parts. So each part will contain 8 bits, and then there is a dot between them. Look at it. So there is a dot between these 4 parts. All this part is popularly also known as an octet. Okay, each of this part, this 8 bit, this 8 bit, this 8 bit, all this part is also known as octet. So this is the first octet, this is the second octet, this is the third octet, and this is the fourth octet. The next step is each octet is then converted into its decimal representation separately. So in the previous example, I have these 4 parts, and then each of these 4 octets, this first octet is first converted into its decimal representation. Again, this octet, the decimal representation is this is the third octet, its decimal representation is this one, and this is the fourth octet, its representation is this one. So this finally becomes my IPv4 address. Clear? The process once again is a 32-bit address divided into 4 equal parts. So each part will contain 8 bits. Each of them will be segregated by a dot. Each of this part is known as an octet, and then we'll convert each of these octet into its corresponding decimal form. And what is the final decimal representation? This one is known as a human readable IPv4 address. This notation is also known as dotted decimal notation. Clear? Now remember, this division of octet and then representing using decimal numbers like this is purely for us, for human beings, because it is not possible for us to deal with 32-bit binary addresses. Remember, for the end host or for the intermediate routers, this decimal is meaningless. For them, an IP address is a 32-bit binary number. Clear? Now remember, we have seen that every IP address contains 2 information. One is the network ID and another one is the host ID. Now since we have divided using a representation like this, 32 bits divided into 4 equal parts. So if these parts has to convey 2 information, one the network ID and one is the host ID, then I have these possibilities. I have the possibility of using my first octet as the network ID, and then I use the rest octets as host ID. Or I can use 2 octets for my network ID, and I can use the other 2 octets for the host ID. Or I can use 3 octet for network ID, or I use the 4th octet for the host ID. So I have these possibilities. So in fact, IPv4 addresses, when it was rolled out to the internet, it in fact used a knowledge like this. It uses this sort of information to divide the IPv4 addresses, and the first avatar or the first incarnation of IPv4 addresses used a scheme similar to like this, and they divided the IP address into a number of classes. Okay, they divided the IPv4 addresses. Remember, IPv4 addresses are size 32 bits, so there is a possibility of having 2 to the power 32 IPv4 addresses, and all these IPv4 addresses were divided into 5 classes. They were named class A, class B, class C, class D, and class E. Out of these 5 classes, class D and class E are not usable in the internet. They were used for specific purposes. For example, class D was used for something called multicasting. Multicasting is sending to a number of nodes, and class E was reserved. It was used for some experimental use. So class A, class B, and class C, these 3 classes were rolled on to the internet. That means these wise 3 classes can be used by general public. So we'll now discuss these three different types of classes. Remember, this was the first scheme or first version of IPv4. Later on, this type of classes notations was removed from the IPv4 addressing scheme. But we should know these three different classes because this is how initially IPv4 addressing scheme started. Okay. The first class A IPv4 addresses were intended for large organizations with many computers. If we go back to the example which we have seen, let's go back to that example and see. So this was an example we use. So this is a network with a huge number of computers. Who would require this sort of network? This sort of network is created by large organizations where there are many departments, many people. So they will be requiring a lot number of computers in their network. A small organization may not need a huge number of computers. So the people who started IPv4, they thought how they divided the classes. They divided the classes based on the size of an organization. They created 5 classes. Out of them, 3 classes were given out for general use. So those 3 classes A, B and C, they divided it in terms of number of computers that can be connected in the network. So they thought that every organization in the world can be classified into 3 parts. Some of the organizations are large or huge, some of the organizations are middle level organizations, and some of the organizations are small level organizations. And so they divided the IPv4 addresses into these 3 classes. Some of the addresses or some of the one class will be for large organization, one class will be for the middle level organization, and one class will be for small level organization. So what is the structure of a large organization? What is the identification of a large organization, or what is the requirement of a large organization? The requirement is that there will be many hosts, there will be many computers in a large organization. So class A addresses were used for large organization. So because they will be using more computers, so more bits are required for the host part. What does it mean? If I use say 8 bits, if I use 8 bits for my host part, then I can represent to the power 8 hosts. But if I use 16 bits, I can represent more hosts. I can represent to the power 16 bits. And because these are for large organizations, they thought that because they may be required to connect more computers, more hosts, so let us keep more number of bits for the host part. So what they did is they reserved 3 octets. 3 octet means 24 bits. They reserve 24 bits to the host part. That means an organization which uses a class A address, they can connect 2 to the power 24 computers in their networks. And the first 8 bits were used for the network part. That means first 8 bits or the first octet will indicate the network ID, and the remaining 24 bits will indicate the host ID for a class A address. Now when they created these classes, they made it as self-describing. That means how would a router, an intermediate router, know that to what class this particular address belongs to? Okay, that there is no other information in that IP address. It's a simple 32-bit string. There is no other metadata to tell that this is a class A address, this is a class B address, or this is a class C addresses. So they made the addresses self-describing. So for class A, they say that the class A address will have F0 fixed in its first bit. So every class A address will have a 0 fixed as the first bit. Clear? Now again come back to this. So in the class A addresses, 8 bits were used for network parts and 24 bits were used for the host part. Of the network part, the first bit 0 is fixed. How many bits are remaining for the network part? 7 bits are remaining. So it essentially means that 2 to the power 7 networks can be represented using a class A address. Or in other words, 2 to the power 7 class A addresses are available for 2 to the power 7 organizations. That means 2 to the power 7 organizations can buy a class A address. Clear? So 7 bits are left for the network ID. What would be the minimum value? There are 8 bits. So minimum value is all zeros. So all zeros is a meaningless thing. Okay, so all zeros cannot be used. What would be the first usable minimum value? The first usable minimum value would be 1. Okay, what would be the last value? The last value will obviously be all ones. First one is fixed as 0 and then all the other ones. That would be the last value. But the last value, the maximum value, is also cannot be used. This is a specific special number which is known as a loopback address. We'll discuss about it in a little bit time. So the first minimum value cannot be used. So the first usable minimum value is this one. The maximum value, this cannot also be used because this is used for a specific purpose. So the maximum usable value is this one. Okay, so this is decimal 126. So we have seen that because we are only 7 bits are available, 2 to the power 7 organization can actually buy a class A addresses, but from this class A addresses, 2 cannot be used. This one cannot be used and this one cannot also be used. So 2 networks now has to be deducted. So what remains is from this value up to this value. This is a total of 126 values. Okay, so that means in the whole world only 126 organizations can buy a class A address. So the initial people assume that there are few large organizations in the world, so let them buy a class A address. So say decision organizations, say big organizations like Microsoft, BJ organizations, and organizations something like Intel, under organization IBM, under organization like Xerox at that time, under organization like say Oracle or some organizations. So like that 126 organizations can buy a class A address. Clear? Why? Because I have only 7 bits left for a class A address. Out of 7 bits also 2 bits are unusable, the minimum and the maximum. So only 126 address are remaining. 126 organizations can buy a class A address. So one organization came and buy a class A address. So left is 125. Another organization came and buy a class A address. So it reduced one more. So like this 126 organization can buy a class A address. You should obviously understand that this scheme, this class A address will obviously not be available since long, because at that time itself there would have been so many bigger organizations and they would have bought a class A address. Clear? So class A addresses are not available anymore. Now, so total 126 organizations can buy a class A address. So what will be what address would the first organization get? So say this is the first organization who wanted to buy a class A address. So first address it will get is 1000. So this is the IP address that was given to the first organization who went to buy an IP address. Why 1001? Remember, first 8 bits, out of this first bit is 0. I cannot use all zeros, I have to use this value. So 00000001. So the decimal value is 1. Okay, the remaining part are for host. We are not discussing host right now, we'll be discussing host after this. So the first value is important here. First octet is important in a class A. So the first value is 1. So the first organization which went to buy a class A address, it was given this IP address 1000. The next organization which went to buy a class A address, what address it had? It had this address 0. First one is always 0, then 0000, 4 zeros, and again another 4 zeros, 1 0, and then the next value. First one was 1, then now the next value 1 0. So this is 2. So the next organization was given an IP address 2000. Clear? Then the third organization went for buying a class A address. It was given the IP address 3000. Like that Up till how many organizations? Up to 126 organizations. So the last organizations that went to buy IP address, it was provided with the IP address 126.0.0.0. Clear? These were the addresses, network addresses that were given to this organization. So class A went and buy the organization A went and say buy this class A address. Now this is a large organization. Now it started connecting the computers in its network. Okay, so class A started connecting the computers in their network. Now remember, its address gives two information. One is the network ID and the other one is the host ID. So now the host has to be numbered. Clear? So how many bits are left for the host part? 24 bits, because 8 bit was used for the network part. So 24 bits are used for the host part. So how many computers can be connected? We have already seen we can connect 2 to the power 24 computers. So I have 24 binary bits for my host part. Clear? The first number is obviously all zeros. All zeros, if I use all zeros, it becomes the network address itself. That means I have bought this address. The first organization has bought this 1000. Clear? So this 24 bits for the host part, if these are all zeros, it is the same address. So all zeros cannot be one to indicate a host. So the first computer that is connected in this address has to start from the number 1. Okay, so say I have bought this first address 1000. I connect the first computer, so the IP address of my first computer becomes 1001. Clear? What will be the IP address of my next computer? 1002. It goes on like this. What would be the maximum value? The maximum value is when they're all ones in the 24 bit. And these all ones are also cannot be used because all ones indicate a broadcast address. What is a broadcast address? We will see shortly. So all zeros cannot be used, all ones cannot be used. That is, the number of hosts that I can connect is 2 to the power the number of bits available for the host part. So in class A I have 24 bits available, so 2 to the power 24 computers I can connect. From that I have to subtract 2. Why 2? Because all zeros cannot be used, all ones cannot be used. So in between I can connect all the numbers I can use for connecting host or computer. So how many computers I can connect? In class A I can connect 2 to the power 24 minus 2 computers. This number of computers I can connect in a class A address. Clear? Let's have an example again here. Say the third organization that went to buy a class A address, it was provided with this address 3000. Clear? In binary it is 01104, sorry, 0000011. First one was 1, second one was 10, third one is 11. So this IP address was given 4 5 6 7 8. So like this 1 2 3 4 5 6 7 8 1 2 3 4 5 6 7 8. So this IP address was given to the third organization that went to buy a class A address. So it was given this IP address 3000. Now it started to connect computers. So what would be the first computer? The first computer would be obviously this string, this whole string, and this one will become 1. Clear? So I have, let's come back here. So my first computer, what is my first computer or the first IP address? First IP address of my network of this is this one. This is my first computer. So the IP address of the first computer would be 3001. Clear? This will be very clear. So if I go along like this, then the second computer, what would be the IP address? The IP address would be 10. So in decimal this is 3002. Okay, if I go on like this, After some times I will have an address like this. Clear? So the IP address would be 300,255. Now this octet is full. Now I will go to the next octet. Remember, I have 24 bits available, so I can use all these 24 bits. So this octet is now full. So the next computer I connect will start from this octet. It will start from this octet. So here 1, then all this remaining will again be 0, 3, 4, 5, 6, 7, 8. Okay, then again it will go on like this. So this IP address is 3010. So again 3011, 3012, 3013, like that, 301255. After that 3021, 3022, 3023. So a huge number of computers can be connected in classes. So I can go on like this, connecting computers one after another and giving numbers to that. What is the last number? The last number is when theoretically when everyone is 1. 1, 2, 3, 4, 5, 6, 7, 8, and 1, 2, 3, 4. This address is 255. Now this address where all is zeros, this address cannot, sorry, let me repeat this once again. Any IP address where all the host bit parts are set to 1, this IP address cannot be used for an individual node. This particular specific IP address is also known as a broadcast address. What is the meaning of a broadcast address? Broadcast address means if this particular IP address is used as a destination address, that particular message will be delivered to every node, every host of that particular network. What does it mean? This essentially means that if someone is sending a message with a destination address, say 3.0.0.1, that particular message will be sent to this particular machine. This machine with the IP address 3001. If someone is sending a message with the destination IP address as 3002, that particular message will come to this particular node, particular machine whose IP address is 3002. Same way in the example where someone is sending a message to 300255, that message will come to this machine, the machine with this IP address 300255, and so on. But if someone is sending a message where the destination address is 3.255.255.255, in that case that particular message will be delivered to all the machines, all the nodes in that particular network. That means that particular message is broadcasted. So this particular address where all the host bits are set to 1 is known as broadcast address. So that's why this particular address is not used for an individual node. Since this address cannot be used for an individual node, the last IP address, the node which has got the last IP address, the IP address will be 1 less than this. So in decimal, the IP address in this example would be 3.255.255.254. So we started with 3001. This would have been the first node, the IP address of the first computer connected to the network, and the last computer in the network, if we had that number of computers, the last computer would have an IP address of 3.255.255.254. I hope this example should have cleared how IP address is allocated in a network. These are some of the essential questions from class A IP addresses. How many networks can be created? This we have already seen. 8 bits are reserved, but out of these 8 bits, first bit is always 0, so we are left with 7 bits, so 2 to the power 7. But again, all zeros are not allowed, and all ones in case of class A is not allowed because it is number 127, which is a special case which we'll shortly see. So all zeros not allowed, all sevens not, all ones not allowed. So it we are left with 2 to the power 7 minus 2, that is 126 networks. How many hosts per network? We are left with 24 bits, so total 2 to the power 24, but the first all zeros are not allowed and all ones are broadcast address. So basically 2 to the power 24 minus 2 host per network. Broadcast address when all the bits of the host part are 1. Okay, when all the bits of the host part are 1, that is initially the network part, then dot 255.255.255, that is the broadcast address of a network. What are the possible advantages of a class A network? So you can think about it. One possible advantage is you can connect a huge number of computers, a huge number of computers you can connect in a class A network. 2 to the power 24 minus 2 computers is a very huge network. What are the possible disadvantages? The advantage is a disadvantage itself. You can connect a huge number of computers, but can you possibly think about any organization which connects 2 to the power 24 computers in its network? It's a huge number. No organization, however big it may be, an organization will not have this number of computers in their network. And because an organization does not have this number of computers, so if an organization buy a class A address, so it can connect this number of computers, but in reality it connects much less than this number. So what is happening? A lot of number of IP addresses are going waste. That those IP address could have been assigned to some other organization, but since this organization has already bought this IP address, and because of this design scheme, this class A address is fixed that 24 bits will be used for the host part, so it has connected to some around 2 to the power 10 number of computers, and then all the other IPs become waste because that organization does not have that many number of computers. Essentially that number of computers, nobody connect that number of hosts in that network. So the major disadvantage of class A networks is that many IP addresses get waste because of how this structure has been created. Now let us move to the second class of networks, class B IPv4 addresses. Like class A addresses were meant for large organizations, class B IP addresses were originally meant for middle level organizations, not as large as the largest organizations, but not very small organizations also. So the people initially thought that class B IP addresses would be used by organizations which have a certain level number of computers in their network. In this class B, 16 bits are used for the network part and 16 bits are used for the host part. In class A, 8 bits were used for the network part. In this case, 16 bit, that means 2 octets. The first 2 octets are used for the network part. The next 2 octets are used for the host part. So equal number of bits for network and host. Just like in class A, the first bit is always fixed to be 0. In class B, the first 2 bits are always fixed to be 10. 10. The first 2 bits are always fixed to be 10. Again, remember why do we fix bits? Because these are used as self-describing. So out of 16 bits for networks, 2 bits are always fixed. Okay, so how many bits are left? 14 bits. 2 bits are always fixed. Out of 16, 2 bits are fixed. So 14 bits are left to indicate network. So we can have a total of 2 to the power 14 networks, that is 16,384. That means this number of organizations can buy a class B IP address. Just as in class A, 126 organizations can buy a class A address. Similar fashion, 16,384 organizations can buy a class B address. Clear? So how many computers can be connected in each of this network? So one organization buy a class B address, another organization buy a class B address, another organization buy another class B address. So how many computers can be connected in each network? Because 16 bits are left, so essentially theoretically we can connect 2 to the power 16 computers per network, but again we have to subtract 2. Why 2? Because all zeros are not allowed and all ones are broadcast address. So basically 2 to the power 16 hosts minus these two, so this makes 65,534 hosts per network. So a good number of organizations can buy a class B address, but is again not a very big number. 16,384 organizations can buy a class B address, and each of these networks can accommodate up to 65,534 hosts. Clear? Let us see some class B questions. The first question is, what is the first network? This should be easy for you. We have seen that 16 bits are there for the network part. The first 2 bits are set to be 10. So this is the first IP address of a class B network. This would be in decimal 128.0.0.0. So any organization who would have bought the first IP address would have got this class B address 128.0.0.0. This is the first IP address for any organization which has bought a class B address. What is a third network? If the first one is 128, the next one would be obviously 129.0.0.0. The third one will be 130.0.0.0. So this is the second network. Clear? And this would be the third network. So this third network will be 130. The decimal would be 130.0.0. The third question is, what is the IP address of the fourth computer of the third network? So this is my third network 130.0.0.0. What is the first computer in this IP address? The first computer is 130.0.0.1. This is the first computer. We cannot use the all zeros. What is the second computer? 130.0.0.2. What is the third computer? 130.0.0.3. What is the fourth computer? 130.0.0.4. Okay, this will be again simple. Once you have started following this becomes very simple in decimal. What is the last network? Can you think of what is the last network? The last network would be when these are all ones. First two is fixed 10, then 1, 2, 3, 4, 5, 6, 7, 8. Then here 1, 2, 3, 4, 5, 6, 7, 8. First two bits are fixed to be 10, then here all ones, then again here all ones. This is the last network. If you convert it into decimal, I guess this should be 191, this is 255, then 00. This is the last network in class B. So the last organization who would have bought a class B IP address, it would have got this IP address 191.255.0.0. What is the IP address of the last computer of the network? So the first computer would have an IP address 191.255.0.1, then 02, 03 like that, and finally the last computer would be 191.255.255, then 254. Why 254? You cannot use 255 because if you set all the bits to be 1 in the host part, it becomes a broadcast address. So 191.255.255.255, that would have been the broadcast address. So the last computer in the last network is 191.255.255.254. Range of values of the first octet. This is our first octet. This is our first octet. So the first octet starts from 128 and it goes up to 191. So the range of values in the first octet goes from 128 up to 191. Then the last question, do you think any class B addresses are available for buying? If you remember the IPv4 class, this type of addresses, class scheme, class A, class B, class C scheme was introduced in the 80s. So this is now 2020. So it's it's almost unlikely that any class B addresses are available for buying. In fact, there are no addresses of class B type available for buying by anyone. So the answer of this question is, do you think any class B addresses are available for buying? And the answer would be a direct no. No class B addresses are available for buying at this moment. Now let us come to the third class of IP addresses, class C. Now these class C addresses were intended for smaller organizations which are of small size, organizations which have much smaller number of computers in their network. That was the original idea. So class C addresses were meant for smaller organizations. In this example, 3 octets are fixed for the network type part and only 1 octet is for the host part. So 3 octets for the network part and only 1 octet is for the host part. So the basic idea is a huge number of organizations can buy a Class C network. So originally it was thought that only a very few large organizations are available, a good number of medium level organizations are available, and there are large number of small organizations are available who would be interested in a IP address. So since it was assumed that there are many smaller organizations, so to enable that more and more smaller organizations should be able to buy an IP address, so a lot of addresses were kept. So many bits are kept for the network part, and only a few bits, only 8 bits are kept for the host part. In Class C, the first 3 bits are fixed. So these first 3 bits are fixed as 110. Okay, so how many bits are left out of 24 bits? 3 octets is 24 bits. 3 bits are fixed, so 21 bits are available for the networking part. So 2 to the power 21 organizations can buy a Class C network. So this is a big number, 2097152. These numbers of organizations can buy a Class C network. Now, how many computers can each of these networks accommodate? Now, remember, this would have been a small number because only 8 bits are available for the host part. So, each of this network can connect 2 to the power 8 computers minus those two. Remember, this minus 2 would come everywhere in the host part. Why minus 2? Because all zeros are not used, it cannot be used, and all ones are broadcast address. So in this example, 2 to the power 8 minus 2 computers can be connected to each of this network. This number of networks in each of this network, 2 to the power 8 minus 2, that means 254. Only 254 computers can be connected in one Class C network. And this is the summary. So Class A, the first bit is always fixed to be 0. In Class B, the first 2 bits 10. In Class C, the first 3 bits 110. Here 1 octet is for network, 3 octets for host part. In Class B, 2 octet for network, 2 octet for host. In Class C, 3 octet for network and 1 octet for host. And this is the range of the first octet. This is important because just by looking at the first octet, the decimal value of the first octet, we can very easily say whether that IP address is of Class A or Class B or Class C. If the first octet decimal value is between 1 to 126, it is a Class A address. If it is between 128 to 191, we can easily say that the IP address is of Class B. And if it is between 190 to 223, we can easily say that this is a Class C IP address. These are the values for Class D and E, but because these two, Class D and E, are not used in the public domain, so we will not be discussing Class D and E. Only these 3 classes A, B and C are available for public in the internet. We should also be aware about some of the special IPv4 addresses. The first one is all zeros. Any IP address which have all zeros, we have already seen this cannot be used as a routable IP address in any of the machines. So all zeros can indicate many of the things. These are some of the reasons why where all zeros are used. Specifically, it can be used at the beginning when a host has no IP address at all, and when it wants to get an IP address. We'll see later on when we use DHCP. There is a particular protocol called DHCP which is used to provide IP addresses by your ISP. So whenever you want to have an IP address when you're connected to the network, at the beginning when you don't have any IP address, this particular IP address 0000 is used. The other special IP address is the broadcast address. This we have already seen, where all the host bits are set to 1, it becomes a broadcast address. Then we have seen that in the Class A part, there is one particular address which starts with 127. Now this 127 is a special IP address. This is used for testing the system. So it is known as a loopback address. It is used to test your own machine. And that means, say this is my machine, and if I am using TCP IP, I have my TCP IP stack installed in my machine. So how do I know that my TCP IP stack is working correctly? This is by sending a message to oneself. That means my machine generates a message which goes through my all layers and then come back to my machine itself. This is a loopback message. So in this case, I give a destination address which starts with 127. Theoretically, all the addresses that starts with 127 can be used. That means 127.001, 002, 003 up to 127, 255, 255, 254. All these addresses can be used as a loopback address. But in real life, everybody use this particular wait address 127.001 as the loopback address. Clear? So this basically is to test the system, the own system. This particular address is also very popularly known as a local host. So this particular address cannot be used in normal IPv4 addressing. Now again, if you can see, all the addresses starting with 127 can be used for loopback testing, but essentially only one address is used. So all the addresses have gone waste. So this is another way how IP address has been wasted in IPv4. Now there is something known as private IPv4 addresses also. Now what are private IPv4 addresses? Private IPv4 addresses are certain addresses which are not usable in the internet. That means these addresses cannot be used in the internet. That means if I given a private IP address is as a destination address, this cannot be sent because internet will not recognize these private IP addresses. So why these particular IP addresses are used? These particular IP addresses are used so that people can use these addresses in their networks, local use, without bothering to buy from anyone. So say I have created a network in my home. I have bought 10 computers and I have created a network in my home, and I don't bother about connecting to the network. Okay, I just want to create a network among my own computers. I am not bothering about whether I connect to the network or not. But because I have created a network, I have to give some IP addresses. Since I am not connected to the internet, why would I bother to buy an IP address from someone? So, but again, I have to give an IP address. So what IP address should I give? So for such purpose, there are certain IP addresses which are known as private IP addresses. So these addresses are available to be used by anyone in their local network. You need not buy such address from anyone. Okay. Now every classes have their own range of IPv4 private addresses. So class A, any IP address that starts with 10, this is a private IP address. So 10, then any number in between. So 10.0.0.1, 10.112, 10.113, 10.0.0.5, 10.20, 30, 10, 10.250, 6, 7. Any address that starts with a 10 is a private IP address of class A. In class B, any IP address that starts with 172 and 16. So 172.16, 11, 172.16.05, 172.16, 20, 30s. Okay, from 172.16 to 172.31. Any IP address in this range, this is a private IP address in the class B. And in the class C, any IP address that starts with 192, 168. Okay, the other two numbers can be anything. Between 0 to here it can be from 0 to 255, here it can be from 0 to 254. So all these range are private IP addresses that can be used by any network irrespectively. So if say I have bought 5 computers and say I have provided some IP addresses here. I have provided here 192.168.0.1, 192.168.0.2 like that, a private IP address. So from the internet, I cannot send the message to any of these machines. That means I cannot say that the destination address is 192.168.0.1 and send to a computer. No, the internet will not recognize it. Clear? So these private IP addresses cannot be used in the network, in the internet. Now this is an important question. Who manages all the IP addresses? We are saying that we require to buy IP address. We do not require to buy private IP addresses. Who provides us with IP addresses? If I want to connect to the IP address, basically I buy a service from my ISP. So normally my ISP will provide me an IP address. But from where this ISP gets its IP addresses? Okay, that means who owns all these IP addresses? Now let's look at it. This organization IANA full name is Internet Assigned Numbers Authority. This is responsible for all IP addresses, whether IPv4 or IPv6. All the IP addresses are managed by these organizations. Clear? So now this organization distributes the IP address to regional authorities. So if I see here, there are region specific registries. So for certain continents, there are certain registries. For example, for Africa region, there is something known as AFRINIC. For Asia Pacific regions, there is something known as APNIC. So these are regional registries. So I can go to any of these regional registries. So this is the regional registries for Asia Pacific. Clear? So if I'm big, I can buy IP address directly. But normally, normal end users do not buy an IP address from these registries directly. Bigger organizations normally buy an IP address directly from these registries. We normally buy an IP address from our ISP. So these regional registries also distributed the IP addresses to different ISPs. Clear? So someone say this is who wants to get an IP address would have to actually fill a form like that. So if I say get IP addresses, I have to apply to get an IP address. So if you look at it, there are fees also. So new member fee, at a glance you can see IPv4 addresses, what's the price. For IPv6 there are different prices for it. So this is how someone gets an IP address. So IANA is the original manager of IP addresses, which are further subdivided or subdelegated to regional registries, which are again subdelegated to different ISPs. Clear? And this is for the Africa region. Okay, now if look at something, you might have been listening about something which says that IPv4 addresses are about to be over. That means within a few years from now, no more IPv4 addresses would be available. Now these things have been going for a long time, but in reality also not many IPv4 addresses are available currently. So if you want to buy an IPv4 addresses, you can actually go to these regional registries and then see how many IPv4 addresses are currently available. This registries also displays the current status for IPv4, IPv6 as well. So this is an example for the Africa region. So if I go to statistics and see how many IP addresses have been allocated, they show me all the statistics by say country wise, by region wise and all. And I can also look at something like IP available IPv4. If I click here, available IPv4, let's see what it displays. So this is the statistics for IPv4 space. So you can see the number of available is reducing. So at this point of time, very few IPv4 addresses are available. Clear? So IPv4 addresses are almost about to exhaust. So when it is fully exhausted, IPv6 will be becoming the most dominant IP addressing scheme. Now anyone who has even a very slight interest in networking, they also know that not many IPv4 addresses are available, that the IPv4 addresses are soon going to disappear. This is something we have heard since a long time. In fact, this thing, the people who were doing research, people who were designing internet, it became important to them way back in the early 1990s that IPv4 was going to exhaust soon. So they started developing a new type of IP addressing scheme, which is now popularly known as IPv6. Now remember, IPv6 was first drafted in the year 1993. It's a long back. It's almost 25 years ahead. Now that means people came to know long back, at least 25 years back, that IPv4 addresses were going to end. And so they came up with the new addressing scheme IPv6. Okay. But it's almost 25 years of developing IPv6, but some of the IPv4 addresses are still available. This is a really funny situation. Long back, 25 years ago, they were saying that IPv4 addresses are going to end. So this they've been saying for 25 years, but still some of the IPv4 addresses are available. How this is available? Because some of the methods that were designed later on extended the lifespan of IPv4. Though it was apparent that these addresses are going to end very soon, but some of the method people developed in between ensured that the lifespan of IPv4 was extended for some more duration. Okay, some of the methods like NAT, which we'll discuss in a subsequent lecture, some of the methods of subnetting, they ensured that this IPv4 address continue for some more amount of time. So at this point of time, IPv4 addresses are still the dominant type of addresses in the internet. That means a good percentage of IP addresses are still IPv4. So these IPv4 addresses will continue for some good amount of years, but at some point of time this will obviously exhaust, this will obviously end, and in that time we have to completely adopt the IPv6 addressing scheme. But since still IPv4 is a dominant addressing scheme, we should be knowing all the details of IPv4 addressing scheme as well. So the first thing is long back in the early 1990s, they introduced a new addressing scheme known as IPv6, which we'll discuss again in another lecture. But IPv4 addresses are still available. But the question is why these IPv4 addresses started to get depleted. This started to get depleted because of the way the classes were initially introduced. We have already seen that, for example, in class A lot of IP addresses were going waste. Only a very few organizations can buy a class A addresses because only 8 bits were used. Out of that 8 bits also only 7 bits could have been practically used, so only 126 organizations could have bought a class A addresses. A few number of organizations could have bought a class B addresses, and a bigger number of organizations could have bought a class C addresses. But in class A and class B, a lot of IP addresses were going waste because normally none of the organization would have connected that big number of hosts in their network. So there was a lot of host address space wastage was going on. So this is to give an analogy, this is something like this. Say you want to buy a pizza, and what is happening in the pizza shop, that they have already fixed the size of the bite. So the class A, they were of large size, something large size like this. Then the class B, some middle size like this, and class C are those small size. These are already prefixed. This size were fixed ahead. So say you don't want to eat this size of pizza, but you have to buy it. If you want to buy a class A, you have to buy this size, and out of this, say you can only eat this part, this amount you can eat. So this amount is going waste. Okay, this was happening with a class A type or a class B type. So a huge number of IP addresses were going waste. So the people who were designing IPv4, they took certain steps. The first step they took is to introduce a new addressing scheme which is known as a classless IPv4 addressing. It's the first step to address this exhaustion of IPv4 addresses. They saw that the classful IP addressing scheme was creating a lot of wastage, so now they developed a new way of addressing. Now this way of addressing is known as classless IPv4 addressing. This is also known as CIDR. Okay, now it uses a notation. This dotted decimal notation is already there, where we use a dot with 4 decimal parts A, B, C, D. Then they use a notation known as /n, where n is a number which indicates the number of bits used for the networking part. So in classless, now in classful, what happened? They fixed the number of bits for networking and host part. So in class A they had fixed 8 bits, in class B they had fixed 16 bits, and in class C they had fixed 24 bits for the host part, and this was causing a lot of number of IP addresses to go waste. So they thought, why do we do that? Why don't we remove this concept of classful? Okay, so they introduced this classless. Now what happened is they can now use any number of bits for the networking part and any number of bits for the host part, depending on the requirement of the organization who wants to buy a IP address. Clear? So instead of 8, 16, 24 is fixed, they can use any number for the network part and the host part. So say someone may want to use only 6 bits for the network parts, and so the remaining bits 32 minus 6, that number of bits would be for the host part. Clear? So 26 bits for the host part. So what will happen in this network? 2 to the power 6 number networks can be there, and in this network in this network 2 to the power 26 computers can be connected. Someone may use 7 bits for the network part, so here 25 bits are available for the host part. Clear? So there's a very small organization which needs to connect only a very few number of computers, say 20-30 computers. So in that case, a huge number of bits can be used for the network part. Say I can use some like 27 bits for the network part, and say that's 5 bits for the host part. So I simply 2 to the 5 number of computers can be connected. So depending on my requirement, I can have any addresses. So the number of computers that be connected depends on the number of bits used for the network part and the number of bits that is used for the host part. So one of these is popularly known as a block size. So when you want to buy something, you say I want to buy this block. Depending on my requirement, I want to buy a block of say 27, I want to buy a block of 7 or something, anything depending on my requirement. So this number n indicates the number of bits used to indicate the network size. So if I have this example, say 192.168.0.0.23/23, this means 23 bits are used for the network part. So how many bits are remaining? 32 minus 23, 9 bits. 9 bits are there for the host part. Clear? Out of 32 bits, 23 bits are used for the network part. So 9 bits are used for the host part. So how many computers I can connect? I can connect 2 to the power 9. Minus 2 would always be there. This should always be there in the host part. All zeros cannot be used. All ones is a broadcast address. So if I buy a block of /23, I can connect to the power 9 minus 2 computers in my network. If I buy an address like this /12, it means 12 bits are used for the network part. How many bits are left for the host part? 20 bits are left for the host part. So I can connect to the power 20 minus 2 numbers of computers in my network. So now I can buy any block. So I can have all this variation /5, /6, /11, /14, anything. This /8, /16 and /24 are similar to class A, class A. So in class A, now if I represent my class A in this classless notation, the class A becomes /8. So what is /8? 8 bits are used for the network part, the rest 24 bits are for the host part. So class A becomes /8, class B becomes /16 and class C becomes /24 in this classless notation. Clear? So this classless notation, again, this is based on the idea of subnet mask. We will be discussing about subnet mask in details. Something about subnet mask we'll discuss in this lecture itself, and we'll be discussing the process of subnetting in the subsequent lecture. So this classless IP addressing should be clear, where we have different notations, where there is a notation /n after the IP address and there is /n. This n number indicates the number of bits used for the networking part. Now we start discussing about subnet mask, which is an integral part of IPv4 addressing scheme. In fact, when we discuss IPv4 address, the subnet mask is an integral part. We have to discuss subnet mask also, because IPv4 addresses and subnet masks come together. Okay, so when we specify an IPv4 address, we have to also specify something known as subnet mask. Now let's see what subnet mask is. Subnet mask, first they look like IP addresses. They simply look like an IPv4 addresses. They are also of 32-bit size. Okay, the same length as an IPv4 address. So the size is same. But they are not IP addresses. They are different. Okay. Now subnet mask in binary is a string of ones followed by some number of zeros. That means the first difference is this is a string of 32 bits, that's fine, but the string is where there are certain number of ones, consecutive ones, then they are followed by certain number of zeros, which are consecutive zeros. That means these are some of the examples of subnet mask. That means I should have some consecutive ones, then I should have some consecutive zeros. I cannot have something like that 1 1 0 and again 1, something like that. So the first difference with a normal IPv4 address, the way it looks is here there should be consecutive ones and consecutive zeros. Consecutive ones followed by consecutive zeros. The size is 32 bits. So if I have 10 consecutive ones, the rest 22 bits would be zeros. If I have 15 consecutive ones, there would be 17 consecutive zeros. If I have 16 consecutive ones, I would have 16 consecutive zeros. So consecutive ones followed by consecutive zeros. There cannot be a break. There cannot be some ones, some zeros, and again some ones and some zeros. So this is how a subnet mask looks like. Now let's see why subnet mask is required and why subnet mask, why this is used, basically why this is used with IPv4 addresses. Now let's first see why do we require subnet mask. Say I give you an IP address. Say this is an IP address, a random IP address. Okay, this, if you look at it, this is a class B IP address. Now if I ask you what is the network address of this IP address, how will you find out? That means remember an IP address contains two information. One is the network ID and another is the host ID. Clear? Now since we have seen how the classes are arranged, so by looking at it I can say that the first two octets are used for the network part and the other two octets are for the host part. So say I can say that this is the network part, is the host part, but how does a router know? How does a router find out what is the network part and what is the host part? So basically, given an IP address, my task is I want to segregate the network part from the host part. I want to say this is the network part and this is the host part. So first say I have converted this to the binary string. So this is the binary string. So I want to segregate the network part. I want to keep this part and I want to remove this part. So if I remove this part, that means I want to, if I make all zeros here and if I keep this remaining part, I get the network part. This is clear? So I want to segregate this part, I want to keep this part and I want to remove this part. Remove means I want to make all the values 0 here. So if I keep this part and I make all the zeros here, I will get the network address. But mathematically, how will you do it? How will you segregate only this part and how will you make all this part 0? Can you find a mathematical function? So I have these 4 octets. I want to keep this part as it is and I want to convert it to all zeros. Okay, so if I convert it to all zeros, I'll be left with this part. So this will give me my network ID in this particular example. So what will be the mathematical function? The mathematical function is I have to mask it. I have to mask it, and to mask it, what I can do, I can logically AND. I can logically AND with the required number of bits with 1. So I require to mask, I want to have these bits as it is. So I will logically AND it with all ones. So if I logically AND this part with all ones, I'll keep this. But if I logically AND all this with zeros, this will become 0. So the network part I want to logically AND with 1. The host part I want to logically AND with 0. So the value with which the IP address was ANDed with is known as the subnet mask. So this IP, so with what value I have ANDed? I have ANDed with this value. This is 255, this is 255, this is 0, this is 0. So the value which I have used to find my network IP address, that part is known as the subnet mask. So I have logically ANDed the network part with all ones and I have ANDed my host part with all zeros. So in this example, the first two octets with all ones, so the first two octets 255 255, the next two octet with zeros, so that two part is 00. Clear? So this is an example. Given this IP address, you have to find the network address. Now first thing you have to look here is that this is a class C network. If you remember, the class B network starts from 128. The first octet is from 128 to 191. Just remember, just by looking at the first octet, we can say whether it's a class A or class B or class C. So 200, the first octet is 200. This is a class C network. So how will you find the network part? How will you mask the network part? So again, I convert it into the binary for part. Now again, you have to do the same, but here in this case I know that 3 octets are used for the networking part, 1 octet is used for the host part. So now I have to logically AND, where the first 3 parts will be logically AND with all ones and the last part will be logically AND with all zeros. So my subnet mask now becomes this 255 255 255 0. That means all ones for the first 3 octets and all zeros for the last octet. So this is the subnet mask for this particular IP address. So if you think about it, for the class, any class A IP address, my subnet mask would be 255.0.0.0, because only the first octet contains the network part. So for class A, the subnet mask will always be 255.0.0.0. For class B, as in this example, it is 255.255.0.0, and for any class C, it would be 255.255.255.0. Clear? So every class has its own default subnet mask. These are not just default subnet mask. So we have already seen for class A, the default subnet mask is 255.0.0.0. That means given any IP address, if I logically AND with this subnet mask, I will segregate the network part. So in the classless notation, this can be designated as /8. The first 8 bits are all ones, the rest 8 bits are all zeros. For class B, the default subnet mask is 255.255.0.0, because if I logically AND these first two octets, I will find the network part. Now /16 in classless notation. And for class C, the default subnet mask is 255.255.255.0, and in the classless notation, this becomes /24. So since we now use the classless notation for IPv4 addresses, so for each of these prefix I have subnet mask. So for /1, what is the meaning of /1? I have only one bit used for my networking part, so the subnet mask is 128.0.0.0. For /2, this is a subnet mask. For /3, this is a subnet. What does it mean? That means /3 means what? I'm using 3 bits. I'm using first 3 bits, the first 3 bits for my network part. Clear? First 3 bits I'm using for my network part. How many bits remaining? 32 minus 3. 29 bits I'm using for my host part. 3 bits for my network part, 29 bits for my host part. So when I have to segregate, I have to logically add only these 3 bits. So 1, 1, 1, 3 ones, and rest will be all zeros. Clear? So 8 bit, 8 bits, 8 bit, 8 bits, 4 octets. So in the first octet, 3 ones and rest are zeros. This is 224. Then rest are all zeros. So for /3, the subnet mask is 224.0.0.0. /9 means 9 bits for networking, so I have to mask only 9 bits. Clear? So when I have to mask 9 bits, the first 8 bits are all ones, that's why 255. In the next octet, only the first bit. So when I use the first only one bit, this is 128. So this is the subnet mask for /9. Clear? So this is very easy to find. The number of bits that are used for the networking part, I have to use that number once in my subnet mask to segregate out the network part. So these are the different subnet masks for the classless notations. Clear? If I look at it, for the normal 24, I would have the 255, 255, 255, 0. So I have one more bit in /25. I would have 255, 255, 255, 128. So this goes on like this. If you follow it, it's very simple. Clear? So this finishes our first lecture on IPv4 addressing. This is a critical lecture, critical knowledge from the point of view of IPv4 addresses. So you should be knowing the different way, the different classes of IPv4 addresses, the problem with classful addressing, what is the problem with this classful type of addressing when classes are used. So to overcome those addresses, how the classless addressing scheme was introduced, and what is subnet mask. In the next lecture, we'll discuss the concept of subnetting. Clear? So this finishes our first lecture. Thank you.